Hi, in this video, we want to take a look at using power transforms to improve our linear models. All right, so previously we talked about using the square root transform and the log transform to improve our models. Now, what we want to do today is we want to make this a little bit more general than what we've done so far. So originally with the square root transform, if you think about it, that is a power of 1/2. During this video, we're going to take a look at natural log, and we're going to see that that corresponds in a special way to a power of 0 in the limit. So when I say limit, I'm talking about calculus. Don't know calculus, don't worry about it, just nod your head at me. Okay, so what we want to do, we want to improve our linear model using a power transform, but we want to let R figure out what is the optimal power for us. And so then we'll go ahead and just run that, whatever is the optimal one, and we're not going to worry about all the details. Now, in real life, when I do this, when I run these transforms, if I get something that's like, let's say 0.53, well, instead of using 0.53, I would go with 1/2, which would be the square root transform. If I saw 0.31, then I would probably go with 0.3, 3/10. If I saw 3.14, I would say the power is pi, something like that. I would pick a number that's more familiar to most people than going with the exact precise decimal value. That's if I need to explain the model, I need to justify what I'm doing. Now, if I'm doing something like machine learning, where I'm never even going to see what's going on, where I'm going to run through the process, I'm not going to look at all the details along the way, more than likely, then what I would do is use whatever the optimal value is spit out by the machine. And I wouldn't adjust it to something that is easier for humans to interpret. But remember, we always have to be able to defend our model in real life. So we always want to be thinking about, hey, is there another way to do this that is easy, that is, operationally just as effective, almost as effective, but better received by my audience? Okay, so first thing we're going to do, we're going to load some data. It's called the response transformation data set from the textbook's website. Now, this data set is definitely generated data. This is not, they use a random number generator and equation. I promise you that. If that's not the case, I'll eat my hat, and my hat is not tasty. So, just know that this example is kind of baked. But it's a good example for the purpose of teaching. It's not real data, but this really does kind of like overemphasize the potential of this process. All right, so something I want you guys to get in the habit of is coloring your data points by an important variable. And so I usually color the data points by the target variable, because that's the one that's the most important to us. And so I go ahead and just use the Residuals colors palette to get a different color for each data point. And then I use the inverse permutation function on the order of the target variable to rearrange the color palette results to the order that I want them in. And then I put that on my data frame. Okay, so what I'm going to do, like in real life, what we do is we try something, we see that doesn't work, and then we try to make it better. That's how real data analytics works. So along that vein, first thing I'm going to do, I'm going to go ahead and just build the vanilla regression model. I'm just going to say y depends on x. I'm going to slap in some data. And now, remember, the most important diagnostic for a linear model is the scatter plot. That is always going to be true. So let's go ahead and build a scatter plot. And hey, what have I got here? If I have a linear model, it should be going along a straight line. That's not a straight line. I don't know what that is. That's something, but it's not a straight line. So I need to do something. I don't want to launch this model. I want something that kind of fits along this curve. I want to figure out some way to do that. Now, you might say a quadratic term. That would definitely be a reasonable choice. But if I have, in general, if I have like, say I have a degree 5 term, polynomial, I'm also going to go ahead and have a degree 4, degree 3, degree 2, degree 1, and then a constant. At whatever power I have all of the successive lower powers also. So if I go with a degree 2, I also need a degree 1 and a constant, which is not a big deal. But if I could just transform it and get 1 power, I might be able to get a better model. And so what I would do in real life, I would try this power transform trick, but I would also consider a quadratic in this particular case. All right, let's go ahead and build some diagnostic plots. And I'm following the author's code. The author does not just use the plot function. Don't really know why, but go ahead. He manually builds it, I think, to try and emphasize certain things. So here we can see standardized residuals. Remember, when I look at the residual plot, I don't want to see a pattern. Do I see a pattern? Yes, I see a smiley face. That means that there's a problem. I don't want to use a linear model unless I really frickin' have to. Sometimes you do. But this would be a case where I would be panicking. I would not want to use a linear model. Furthermore, I mean, it looks like to me on the right that the residuals are a little bit more spread out as you go from left to right. So that might be another issue I might have to deal with later. Now, next time we're going to look at the square root of the absolute value of the standardized residuals. And we do this to kind of put everything on a similar scale. A lot of times, this plot is easier to spot patterns that we don't want to see. Well, here I see a pattern. Looks like kind of like a warped W. And that's just coming from the smiley face with absolute values bringing it up in the square roots. All right, let's take a look at the target variable. All right, so here we're going to go through and we're going to kind of exhaustively take a look at the target variable and the predictor variable to make sure we fully understand what's going on. So let's go ahead and use the density function. And there's a bunch of different ways to do the density function. One thing you'll notice is that something that's different than most of the time when you see people using density is I cut it off from between the maximum and minimum observed values in the data. I don't let densities go any farther. That's just to make sure that I keep everything within what I actually observe. The kernel is Gaussian. That's a good default for a lot of unimodal data sets, even if it's not Gaussian. If it's unimodal, a lot of times that's a good choice. Unimodal and data along a continuum, data of the real numbers. And SJ is the bandwidth parameter. And then we just go ahead and plot it. Take a look. Okay, so if I have a normal distribution, I should see a bell shape where the tail on the left looks like the tail on the right. Well, I've got a tail on the right, but over here, I don't have a tail on the left. All right, so this looks skew right to me. So if this is skew right, then I might want to transform it. Now, I might want to go, hey, you know what, let's go ahead and try a log transform. That would be a very reasonable choice at this point. But let's go ahead and dig into it a little bit more. Let's take a look at the box plot. Okay, so for the box plot, remember a box plot is a 5-number summary. So we've got minimum, we've got the maximum, we've got first quartile, third quartile, and then the median. 5-number summary. Okay, so for this purpose, what I really want to see is where are the concentration of data? Where's the concentration? So I want to see what's the distance between minimum, first quartile to median, median to third quartile, and then third quartile to what's practically the maximum. Here we're going to, since these are outliers under the criteria set by the default criteria under the box plot function, pretend that these 2 points are here and treat this as the maximum. And I want to think of it as I've got a fourth of the data here, a fourth of the data here, a fourth of the data here, and a fourth of the data here. Well, you can see that this is kind of stretched out. So this is much longer than what's over here. And here, this is going to be higher up, a higher vertical difference than over here. So this indicates that it's a skew right distribution. All right, so now let's go ahead and look at the QQ plot for the normal distribution. And if this is normally distributed, then these points will be close to this dashed line. Well, the middle is almost always going to be close to the dashed line, by the way. So you really don't focus on this. If you see a deviation in the middle, that's usually like a really bad sign. Or if you have small data, things can not adhere to it as well, just because you have small data and things haven't converged yet. But I see that I've got like a tail above the line on the left and the tail on the right is above the line. I really want to look at the tails. If I see a large portion of tail above and below on each side, that's like a red flag to me. So here, this is actually consistent with a skew right distribution. I sometimes go over it, most don't, how to analyze skewness and kurtosis from a QQ norm plot using these tails, but it's all, I think you should just look at the density plot or the histogram, honestly. It's easier to interpret. Okay, so let's go ahead and look at our predictor variable now. So once again, we're going to use a density function to estimate the density. And we're going to go ahead and use a special function to figure out what the bandwidth is going to be. This function, this bw.sj, is going to go through and try to find under the sj bandwidth parameter, what is the optimal value? And we just set what the upper and lower bounds of the parameters are. And then we drop it into the density function, within the density function, and then we put the density function into plot and we take a look at what happens. All right, and that's close enough. Remember, density plots will never look perfectly like a bell curve unless you start really playing around and dinking with stuff, and then you're just doing nothing meaningful. So you'll never get a perfect actual normal bell curve from a density plot, but that looks pretty darn good. If I see that it's unimodal and it's symmetric, I'm happy. Let's go ahead and look at the box plot. For this one, we want to see that each side of the box have about equal vertical difference between the lines, and that's not too bad. And we want to see the vertical distance from here to there, from there to there, to be equal. So, and if it's symmetric or approximately symmetric, the the length of the two sides of the box will be about equal. The length of the whiskers will be about equal. Let's do a QQ norm plot. Oops. And that's pretty close. Deviating a little bit more than I'd like, but I can see that it's it's pretty symmetric and it's unimodal for almost every use. I can go ahead and call this normal. In real life, you will never actually see perfect normal data if you have enough of it. All right, so what I want to do, I want to actually find the optimal power transform. So previously, we used the square root transform, which was a power of 1/2. Well, what I want to do now, I want to find a really good power transform that it could be a half, could be 2/3, could be 1/10, could be 5, it could be like any value. And what I want to do, I just want to take it and I want to, then after I find it, I want to transform the target variable and then run with things. So I don't see any problems with a predictor variable because that looks approximately normal, but the target variable clearly is not. I'm going to want to do something special with that, something different. And the ALR3 package has a function called the inverse response plot. And what this will do is that this will go through a bunch of values and this will try to find an optimal one for us. Now, this function is depreciated, as it says very clearly here, but it's exportable from the ALR3 package without having to load the entire package. In general, I tried not to load packages if I can avoid it, because that can lead to package confusion. I don't want package confusion. I mean, that anything with the word confusion sounds bad, right? So I'm going with this one because the non-depreciated version of the function, I have to actually load the full package altogether. For my purpose, I really don't see a difference. I ran both of them before I made this video. I don't see a disadvantage to the inverse response plot as it stands right now. I'm sure down the road, it might be an issue. Okay, so if I look at the teal corresponds to a power of 1. Well, what's a power of 1? That's just going to be a straight line, because we're not changing anything. And then, you know, if we look at 0 for the power transform, kind of looks like a log, maybe. A -1, we get this curve. Now, it's saying that about 0.33 is the one to go with. And we can see that the points are pretty tight to 0.33. Okay. Well, let's go ahead and take a look at the residual sum of squares. And we can see that 0.33 is an order of magnitude, or 2 orders of magnitude smaller than the other 3. So that looks at least reasonable. Well, what if we want to go ahead and consider more values? Because here it's just doing 0.33, -1, 0, and 1. What if I wanted to try some other values? Well, here's a grid of values I can pick. So I got -1 and 1, -0.5, a half, approximately -1/3 and 1/3, -1/4, 1/4, and 0. So these are all values that correspond to fractions that are rather natural to be using. Now, when I do this grid search, if I end up picking a value at the end of the grid, I definitely want to repeat with like additional values. So if I saw that 1 or -1 was the best value in the grid, I would also want to start looking at like 1.5, 2, 3, and so on. So now let's take a look. And so we can see all the grid values through here, and it computes the optimal of being 0.33. And we see the same plot for 0.33. And I use the which.min to pull out the best one in the collection. Yeah, so if you look at the code, I set M to be the output from the plot, the output from the calculations. And then I went ahead and I plotted that. All right. Okay, so now just to get a visual feel, let's go ahead and plot the lambda values and the residual sum of squares from the inverse response plot. And we can see that it gets pretty small around 1/2 and 1/3. So 1/4, 1/3, a pretty small values there. All right, now the Box Cox transform. This is slightly different from the power transform. How it's different is that, so the power transform is we take the variable and we take it to some exponents, like I have here with lambda being the exponent. The Box Cox transform is we make this fraction with on top being the power transform -1, and then we divide. Oh, I have an extra parenthesis there. Shame on me. All right, then we divide by the exponents. So power transform -1 divide by exponent. Okay, why do we care? It works out that if you start doing a little bit of calculus, some baby limits, some super easy limits, then what'll happen is you can convert this over to the fraction that goes to the number e in the limit. if you remember that from that portion when you're studying limits and power series and Taylor polynomials and stuff like that. All right, so why do we care about this is because when I take a limit of this as lambda goes to 0, we end up getting log of y. All right, well, if I can take a limit as it goes to 0 and it gives me something coherent, that means that that's a more useful format. Because, so think about what's anything to the power of 0? It's 1, okay? It's 1. Anything to the power of 0 is 1. Even 0 to the power of 0 is 1 in the limit. All right, so because of that, I'm able to extend my power transform to include the number 0 and all the super small positive and all the super small negative numbers that are close to 0. And so this gives me a little bit more freedom that I don't have to worry so much about putting something to the power of 0. Because if I put something to the power of 0, if I put something to the power of 0, I get 1 every single time. But if I put something to the power of 0, subtract 1, and then divide by the exponent, I get something that's really close to log of that number. I mean, this is a really weird fact. Assuming that the number's not actually 0. If you plug in actual 0, then things go wrong because I get 0 on top of 0, and we know that we can't do that. All right, so now, if I look at the Box Cox transform, I overshot the part of the document that I wanted to look at. There we go. The mass function has a function called Box Cox that what this will do, this will find the 95% confidence interval for the optimal Box Cox transform for us. And before writing out, when I wrote out the code before making the video, I found some reasonable values. And what it does, it goes ahead and it prints us it. All right, so now this is going to be the log likelihood. So hopefully you remember from mathematical statistics the importance of likelihood and log likelihood. Well, I want to maximize the likelihood, which is equivalent to maximizing the log likelihood. And I can see a value close to 0.33. All right, well, just to get a better feel for this, let's go ahead and zoom in. So in this situation, I've just made the sequence over a narrower range. And I can see it zoomed in. Now, I could keep on getting like super like fine details and go into like more decimal places if I want to zoom into this more, but this is good enough. I can see that about 1/3 is going to be close to the estimated optimal value. All right, so what I want to do is I'm going to take my target variable y. So my target variable is y. I'm going to take that and I'm going to put it to the power of 1/3. And I go ahead and store it in my data frame. Now, something I did, you don't really want to put like slashes in column headers. You don't want to put slashes. You want to avoid punctuation inside punctuation and special characters and white spaces inside column names. In general, that's a good rule of thumb for Python, for SAS, for R, for anything, that you really want to keep it to letters, numbers, and then underscores, possibly periods. So I put 1_3 for 1/3. It's clunky looking. I don't like the look of it. It's aesthetically unappealing to me, but it's a good label. I thought about using 13, but I was like, no, I'll put underscore. So what I'm going to do is I'm going to go through and I'm going to, now that I've transformed the variable, I want to double check, does this look like it's going to work? If it doesn't look like it's going to work, I'm going to abandon this and try something else. So I'm going to go ahead and find the optimal bandwidth again, and then I'm going to plot the new density that I get. And the new density, wow, that looks like a bell curve. And wow, that looks really like a bell curve, like so much like a bell curve. I I think this is fictitious data, that this was randomly generated. Don't know for certain. I'm not the author. I'm not going to bother calling them up, but I bet money on it. All right, so now let's take a look at the box plot. Like, holy cow, this part is, looks the same as that part. This part looks the same as that part. The two sides of the box are, equal to each other in width. The two lengths of the whiskers are equal to each other. That looks like it's what I want to have. Let's go ahead and do the QQ norm plot. I bet you can guess what the outcome is going to be. It looks pretty good. A little bit. Actually, I'm kind of surprised that this is a little bit farther off than I thought it would be. This is close enough. I'm not going to worry about it. This is a little bit more than I thought. But que sera, sera. All right, so now let's go ahead and build a linear model. So now you'll notice that what I did was I changed the y value to 1/3 just because I want to let R do any transformations for me if it can. I could have used the transformed version that's stored in the data frame, and that would be a better way to go if I had to do if I was repeatedly doing a lot of models. But for this situation, this is good. It's small data. There's advantages and disadvantages with transforming the data and putting it on your data frame. The other option is to let the functions in R do the transformation for you. For small data, I do the transformations inside the functions because I'm lazy. All right, so I go ahead and build my new linear model. And I'm going to go ahead and plot it and look at the line. And that is tight. That is tight, tight. Let's go ahead and look at the summary. All right, it's 0.996, 0.996. That is extraordinary. You will never see anything that good in real life. All right, so I hope this convinces you that the power transform and the Box Cox transform can greatly improve our models. That's all I got for you. Take care and goodbye.